Let us understand mass and energy. Einstein proposed that mass is a form of energy and it can be converted to other forms of energy. He gave the following mass-energy equivalence relation: E equals to mc square. Let's see how much energy is equivalent to 1 gram of mass. Assuming C equals to 3 into 10 to the power 8 meter per second, E equals to 10 to the power minus 3 into the square 3 into 10 to the power 8 joules equals to 9 into 10 to the power 13 joules equals to 9 into 10 to the power 10 kilojoules. Thus, a mass as small as 1 gram can release such an enormous amount of energy. However, converting mass into energy is not that feasible, but this concept is very important in the study of nuclear physics. Till now, we have learned that nuclear is made up of protons and neutrons. Therefore, it may be expected that the mass of the nucleus is equal to the total mass of its individual protons and neutrons. Let us study about nuclear binding energy. It may be expected that the mass of the nucleus is equal to the total mass of its individual protons and neutrons. However, the nuclear mass m is found to be always less than this. The difference in mass of a nucleus and its constituents delta m is called the mass defect and is given by delta m equals to z into mass of proton plus a minus z whole into mass of neutron minus the nuclear mass. Measurement shows that the mass of an atom is less than the total mass of the constituent nucleons. Mass defect delta m is the difference in mass between all the constituent particles of the atom and the atom itself. Delta m equals to summation of mass of final particles minus mass of initial atom. The mass defect delta m is also related to the binding energy given by Be via Einstein's relation. Be equals to delta mc square, where c is the speed of light, a constant. The binding energy Be is the energy required to break the atom into its constituent nucleons. Be equals to delta mc square, where c is the speed of light, a constant. Binding energy per nucleon EBN is the ratio of the binding energy EB of a nucleus to the number of nucleons A in that nucleus. EBN equals to EB by A. The binding energy per nucleon can be plotted versus atomic number. From the graph, deuterium 2H or D has a binding energy of 1.15 mega electron volt per nucleon and tritium 3H or T has a binding energy of 2.9 mega electron volt per nucleon. Note, the curve of binding energy per nucleon EBN has a long flat middle region between A equals to 30 and A equals to 170. In this region, the binding energy per nucleon is nearly constant, that is 8.0 mega electron volt. For the lighter nuclei region, A less than 30, and for the heavier nuclei region, A greater than 170, the binding energy per nucleon is less than 8.0 mega electron volt. This feature of the binding energy curve means that nuclei in the middle region of A from 30 to 170 are more tightly bound than nuclei with A less than 30 and A greater than 170. Both fission and fusion increases the binding energy per nucleon and in doing so releases that change in binding energy to the surroundings. Energy from fission and fusion involves the release of binding energy. The total mass of the fission product is less than the original U-235 atom, that is fission. The reduction in mass is released in the form of energy E equals to mc square. For example, the fusion deuterium-tritium reaction in which two deuterium atoms combine to form a tritium atoms result in a total of 4.1 mega electron volt of binding energy.